Okay, good morning.
Good
Good
morning,
morning,
sir.
sir.
Okay, so I think everybody is here or one, two, three, four. Okay, आ गए सब प्रवीण भी आ गए पांचों लोग आ गए सो आई कैन स्टार्ट तो वो जो मैंने पोस्ट किया था स्लाइड्स वो तो मिल गई सबको हाँ हरीश बोलो क्या हुआ हर्ष 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 सॉरी हरीश लिख रहा था ओके सो आई थिंक before starting the class I just want to tell you again that please stop me at any point when I'm giving a lecture and because I'm not sure what is your real background, so I will try to give you certain concepts, and if there is an issue then just let me know. Okay, so let me share my screen. Can you see my screen now?
Yes, sir.
Okay, good. Okay, so let me minimize this so that okay. Okay, so computational number theory. So I will start with the very basic thing, which probably you know already, our number system, And what is there in our number system? We know that first thing that came across was set of natural numbers 1, 2, 3, 4, 5, and so on, right? Keep on, you can keep on going up to infinity. Set of natural numbers were discovered initially as a result of counting, counting certain things. And then, there were certain equations, for example, x plus 2 is equal to 0, which has no solution over natural numbers, right? So this set was extended, to what is known as set of integers. Okay, so set of integers, all numbers of the form 0, plus minus 1, plus minus 2, plus minus 3, and so on, right? Set of integers were discovered, 0 I have given, but sometime actually, people also include, write down n0 as a set, which is singleton 0 union set of natural numbers, sometime they write it like this. Okay, uh, similarly we also write sometime the following notation: z plus means, you are having integers, set of integers, minus singleton 0. You delete singleton 0, so that is denoted by z plus. In some books you will find this notation, Okay, so then there were certain equations which we cannot solve even in this set of integers case. Can you tell me, anyone tell me what kind of equations we cannot solve over this domain of integers?
All those equations that have solution as a rational number.
Correct. So we can have one equation like 2x is equal to 1, right? So this equation has no solution. So we need to extend the set. And these situations are arising, from your daily need, daily business need, So that means we need to extend it to what is known as set of rational numbers. Okay. Rational numbers of the form P by Q, where P and Q are integers. And of course, Q is not equal to 0, set of all rational numbers of the form this, these are known as set of rational numbers. Okay, now again there were equations which we cannot solve here, right? And the equation is x square is equal to 2. We cannot solve this equation here, right? So we need to extend this set further, and this resulted in what is known as real numbers. Real numbers means, you have rationals as well as irrational numbers, collection of that, so essentially your real line, 0, minus infinity, plus infinity, that kind of thing is your real line. Okay, this side is minus 1, this side is plus 1, and so on. Set of real numbers. Then there were equations which we cannot solve in reals also, like x square plus 1 is equal to 0. So this set was further extended to what is known as complex numbers. Now, one thing I should tell you here, set of complex numbers are normally defined by a plus ib, such that a and b are reals and I is root of the equation x square plus 1 is equal to 0, right? So I is equal to square root of minus 1. So this is nothing but set of complex numbers. Now my question is there any further equation which we cannot solve here with real coefficients? Yes. Is there any further equation that we cannot solve? Please answer. Anyone can answer, Ashish or Basant or anyone, Praveen. Are there any equations that we cannot solve in complex?
So I don't see any right now.
So you mean to say any equation that I take, we will be able to solve over the field of complex numbers, right? So you are right actually. That's why C is known as field of splitting field. Means any polynomial will factor completely into the you can factor it into the factors. Complete factors can be obtained for any polynomial with real or complex coefficients. So that's why it is known as field of splitting field. Now actually one another important thing, that between natural numbers and integers, so there is a connection between Q, R, and C. Can anyone tell me what is a connection between Q, R, and C? Is there any common algebraic structure through which I can call Q, R, and C? Q, R, and C, which is not so. Each of these three sets, Q, R, and C, they have the property which is not part of natural numbers or integers. So
So they are continuous, they are not discrete.
okay, that is one observation. Good. Further, algebraic is property I am just asking you. Now, actually, you see that in Q, R, and C, if I take any two numbers, I can add them, I can multiply them, I can subtract them, and I can divide them, right? We can do all these four operations.
Sir, in last class you said that the Q and R and C, all these form fields.
Yes, so they form field. The field is a set where we can do all these four operations, right? So Q, R, and C are examples of field. In fact, they are examples of infinite field. The number of elements are infinite here. Okay, so the infinite fields. Fields where we can do all the four operations. Okay, so Q, R, and C are known as field. Actually, later on we will see, that when we are solving certain equations, so basically, it's really very important. How do we solve? So 1 minute. This page. So this is a yes. Any question? Any question? Achha, one more thing I just want to, yeah.
No, sir.
Okay. One more thing I just want each of you to keep a piece of paper, because sometime I will ask you to do some calculations, Okay, so keep a piece of paper and pen ready actually in all the lectures, so that when I'm teaching, I may give you some nice small question to work out, so that you also do and learn. It's not a monotonous learning, but you can also see what is happening. Okay, fine. One set that is very common, and that is known as is set of prime numbers, right? 2, 3, 5, 7, 8, 9 नहीं है, 10 नहीं है, 11 and so on, right? Set of prime numbers. So any idea how many prime numbers are there? Any idea how many prime numbers are there? Infinity, correct. Infinite. So actually, how will you prove this fact that there are infinitely many prime numbers,
Because set of prime numbers is a subset of natural numbers, and set of natural number is infinite, so set of prime numbers is also infinite.
No, that argument is incorrect little bit, because you see, from the set of natural numbers, I can take only 5 elements, right? Or 10 elements, I don't know, maybe at what point it stops. So, there will still be a finite number, right? So, which will not prove that it is infinite, So essentially, there is a nice proof given by Euclid. Euclid's result. Euclid's theorem. It says that cardinality of P is infinite. Proof is very simple, so I will just say you in one word. Suppose they are finite, okay? Suppose they are finite. That means the numbers are P1, P2, P3, say Pn. Suppose n prime numbers are there total. Suppose they are finite. In that case, we consider another number, which is P1, P2, product of P1, P2, Pn, and plus 1. Now this number will also be a prime number, right? which is not in the set. So basically what I'm saying that whenever there is a set is finite, we are able to produce another prime number. So this is a contradiction, you know. So basically that means the total number of prime numbers are infinite. Okay. So this is a very one line proof actually. Another important property that we would like to say in number theory, and that is fundamental theorem of arithmetic, you know. Fundamental theorem of arithmetic. Okay, and it says that any integer n greater than 1 can be written as p1 raised to power alpha 1, p2 raised to power alpha 2, pn raised to power alpha n. Partial product of where pi's are prime numbers, right? And alpha i's are non-negative integers. Okay, so any natural number n greater than 1 can be written as product of prime factors. This is a very, very fundamental result. Okay, and now if I ask you one very simple question, actually, if I ask you the following question, that in terms of prime, you know, primes are really very, very important objects, you know. Can you find a formula for nth prime? If you look at here, 2, 3, 5, 7, 11, right? So first prime is 2, second prime is 3, third prime is 5, fourth prime is 7, fifth prime is 11, and so on. If I ask you this question, what is the formula for nth prime? I need a formula so that I can tell what is the nth prime, right? Any idea about it? I would like to listen your ideas, you know, here. Are you aware of any such formula?
So it's I think prime to some power plus 1.
No, not really. Any other thought process?
No, sir, I'm not aware of any formula like.
Okay, so let me give you some idea. Actually, it's a really interesting thing. So we can actually ask, you know, another simpler question actually first. How many primes are there less than a given number x? So suppose I denote this by pi of x. So pi of x means how many prime numbers are there less than x. Okay, for example, pi of 1 will be 0, right? एक से छोटा तो कोई प्राइम नंबर है ही नहीं. Pi of 2, 1 और 2 में एक ही प्राइम है, so pi of 2 is 1, right? You can actually see that pi of 20 is 8. 1 से लेकर 20 तक में 8 प्राइम्स हैं, ठीक है? So now the question is, can you find a formula for pi of x? I hope you got the question right. What we are asking, how many primes are there which are less than a given number x? And answer to this question was given by Carl Friedrich Gauss. Gauss has done a lot of work in number theory. And when he was actually a child only, he was looking at tables of log, and he came up with a nice formula, So before describing that formula, I need to talk about few basic things. So maybe I should mention nicely the formula. It is known as prime number theorem. Prime number theorem, and it turns out that it says that pi of x is asymptotic to x divided by log x. Do you have any idea what is the symbol, Vigil? And what is the meaning of it?
Approximate.
Not approximately. I should say this symbol means, if you know a little bit of complexity in computer science, limit x tends to infinity, pi of x divided by x divided by log x is 1. So, so they work exactly, in the same way. So asymptotically means, so this limit is 1. So the asymptotic behavior, as x approaches towards infinity, the behavior of pi of x and x log x divided by log x is same, right? So this is the question. So do you have some idea about complexity notations like big O notation and so on?
Oh, yes, sir.
Yes, sir. Okay, so good. So then you may be able to recall this, that anyway, do you know how to prove this fact? No idea, right? Any idea about the proof of this fact? Anyway, so okay, no problem. We will come to this. So let me actually give you some idea about these complexity notations I will recall. Okay, so that you know what are the things. Okay, so I hope you understand about this prime number theorem, which says that that number of primes less than x, the formula for this, as x tends to infinity, is behaves in the same manner as x divided by log x. Okay, so this is a common thing. Now let me actually now I think before going to some more complexity notations, I would like you to do some calculations. By the way, do you know, in terms of computer science, if I want to store these integers, so basically what happens, when we are dealing with numbers in number theory, so many times, suppose I have factorial 100. How big is this number, any idea? How will you store a large number in computers, factorial 100, how will you store that? So essentially there is an issue. If in a 32-bit machine, in a 32-bit machine, we know that we can store numbers, from the range minus 2 raised to power 31 to 2 raised to power 31 minus 1, right? This is the range we can store numbers, So basically factorial 100 will require 158 decimal digits, or approximately 525 bits, okay, to store factorial 100. So basically the problem that we have when we are storing large numbers, okay, there is an issue in computers, right? I mean, so we may have 64-bit machines as well, which can have better storage capacity, okay. So okay, so basically now let me show you some of the base arithmetic. Okay, one minute. Yes, base B, arithmetic, base B arithmetic. So that means, so our number, say for example, 123. What is 123 means? 1 into 10 square plus 2 into 10 plus 3 into 10 raised to power 0. This is 10 raised to power 1, right? Okay, so this is the base. Base here is 10. Sorry, not the other one. Sorry. So yes, so base here is 10. Okay, so base B arithmetic. Suppose I want to add two numbers, or how do we store? So basically, representation of big integers in computers. How do we do this? So normally we use base B. Okay, so for 32-bit machine, base is 2 raised to power 32, 2 raised to power 32, and for 64-bit machines, base is 2 raised to power 64. Okay, so these are our base. So normally we don't store decimals, but we store in different base. So let me show you an example. Suppose our base is 2 raised to power 8. 2 raised to power 8 means 256. So we know that there are 256 ASCII values, Okay. So suppose your integer n is 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, 7, 6, 5, 4, 3, 2, 1. It's a large integer, right? It's a large integer. So I can write it down this as 43 into base raised to power 6 plus 220 base raised to power 5 plus 84 base raised to power 4 plus 98. So into, actually all these are into, okay, 98 into base raised to power 3 plus 254, sorry, plus 145 into base square plus 244 into b plus 177. In other words, we write it like this: 43, 220, 84, 98, 145, 244, 177. This is in base B. So are you aware of this arithmetic? How do we find this actually from an integer n? If I have to find, we know that we can verify it easily, right? So if B is 256, I can substitute it here on the right side. I will get, and we will get the left hand side, right? So 43 is known as most significant, you know.
Yes, sir.
Okay. So 43 is known as most significant. I'm just recalling most of the stuff, right? So most significant, right? And 177 is the least significant. Okay. So in fact, we store these numbers in an array form. So I can show you array index. Zero, 1, 2, 3, 4, 5, 6. So digits are 177, 244, 145, 98, 84, 220, and 43. Right. So this, right. Array index and the digits are there, right? And normally we store in computer the sign, the plus sign or minus sign. So we take another one, you know, additional bit where 0 means, you know, positive, and 1 means negative number. Okay, I think so. You must be aware of this representation of large integers in computers is done like this, because whenever we are handling in number theory large numbers, it is difficult, you know, so we need to find a way to do the thing. So normally we store in different base. Now I think I will show you how to convert as an example. I will give you 3 examples now. Okay. Basically addition, subtraction, and conversion. So first let us look at the conversion. Okay. So example, convert 1, 2, 3, 4, 5, 4, 3, 2, 1 to an integer in base 256. So b is equal to 256. So how do we convert? Okay, so let me show you step by step how we are going to do it. So one side I will take the input. 1 minute. Input, then operation, and BLE representation. I'm going to do it one by one so that you know how it is done more algorithmically. So first bit is 1. Okay. So every time what we are doing actually, in fact, you know, I should give you some. Anyway, so take 1 as the input, and we are going to do some operations. So initially, in fact, even before that, there should be initialization. So we have operation is initialization. So first we initialize the BLE representation. So we have, base B initialization. Now the input is 1 here. Okay, the first bit is 1 here. So what we do, multiply by 10 and add 1. Two operations we are going to do. So when we multiply this by 10, since there is nothing, it's kind of 0, so we are not getting anything. But when we add 1, we will get 1 in base B. Okay. So we got 1 in base B. Next input is 2. So we write down 2. Again, multiply by 10 and add 2. So multiply by 10 will give us 10 and base B. When we add 2, we will get 12 at base B. Right? Any question? I'll just take some more. Yes.
Sir, can you redo the second step
Yeah. Sure.
after initialization?
Okay. So the first initialization is blank, right? So when input is 1, I am multiplying by 10. So there is nothing here, right? So basically there is no, it's kind of 0. So when you multiply by 10, it will remain 0, nothing. It will remain nothing, right? And when we add 1, so actually we get 1 here. Okay?
Okay, sir.
Okay. Okay. In the second step, so after that, when the next input is 2, we again multiply by 10, which so 1 into multiply by 10 is 10. And when we add 2, it is 12, right? Got it?
Yes, sir.
Okay. Now, next input is 3. When the input is 3, again multiply by 10 and add this time, add this 3. So when we multiply by 10, this value will be 120, right? 12 will become 120 and add 3. So here it will become 123. Correct? No problem?
Yes.
Now we need to be careful. अभी क्या होने वाला है? Actually, now we have 123. Okay. Next input is 4, right? 1, 2, 3, 4. So next input is 4 here. Now I am multiplying by 10. Now when we multiply by 10, 123 will be what?
Greater than 256.
Yeah, so now things will come. So I think I can write it down here, some calculations. 1230. यहाँ तक तो 120 तक में तो it was less than 256, so no issue, right? 123 तक तो कोई issue नहीं है. When you multiply by 10, so now it is 1230. So if I am writing 1230 divided by 256, if we divide it by 256, what we are going to get? 4.8046. I'm using calculator here, so you can also use calculator here, right? Whatever. So when we divide by 256, we get this. So 4 एक extra आ जाएगा ना, ये बाहर आ जाएगा, right? And so basically, I need to also 8046875 को हम 256 से गुणा करेंगे तो हमारे पास क्या आएगा? आई एम जस्ट डूइंग इट ऑन कैलकुलेटर. 4 into 256, so we will get 206. Okay, so this thing will be here 4,206 base B. Got it?
This is taking modulus.
What?
So this is same as taking modulus, mod operator.
Mm-hmm.
Reminder that So the
Yeah.
remainder, when we divide 1, 2, 3, when we take mod of 1230 by 256.
Mm-hmm.
So I also got 206.
Okay. Okay, so let us check for the next step, what happens. Now we take next input is 5, right? So we'll take 5 here. So 5 के केस में भी क्या होगा? Multiply. Oh, forget actually. Before 5, actually I forgot, Add 4 करना था ना? Add 4. If we add 4, what will happen?
Two 10.
Correct. Good. So now input is 5. Multiply by 10 first. Multiply by 10 करेंगे तो यहाँ कितना आ जाएगा?
2100 divided by 2.
So we can do the calculations here.
8.
Yes, 2100, right? Divided by 256. So कितना आएगा?
8.203.
Okay, मैं अपने में कैलकुलेट कर लेता हूँ कैलकुलेटर में. This divided by 256, it is 8.203125, right? तो ये 8 कहाँ चला जाएगा? यहाँ तो 10 से गुणा हो जाएगा ना, 40 हो जाएगा. 40 और ये प्लस 8 ये हो जाएगा तो 48 हो जाएगा, राइट? मल्टीप्लाई बाय 10 और यहाँ पे 2100 में बचेगा 0.20. तो 0.20, so minus 8 is this into 256. This will give us 0.203125 into 256 will give us 52. So this is 52 in base B, right? ये रफ कैलकुलेशन हो रहा है हमारा. Okay, and so multiply by 10 and then add 5. Add 5. So when we add 5, this remains 48 and this will become 57. Base B. क्या इसको कंप्लीट कर सकते हो? मेरे को बताओ फाइनल आंसर क्या आ रहा है. बता सकते हो फाइनल आंसर क्या आ रहा है? Or should I do it here one by one anyway? Now we take n is equal to 6. N is equal, sorry, no, 6 तो है ही नहीं. I am sorry. 5 के बाद है 4, right? 4 है. 5 के बाद 4 है, right? So next input is 4. So we multiply by 10. Okay, when we multiply by 10, so this time this side will be 40, which is again more than 256. This side will be 570, which is again more than 256, right? So I can compute 480 divided by 256. कितना आएगा? $480 divided by 256. It turns out to be 1.875, right? तो एक 1 इधर चला जाएगा, right? We will have 1, okay, and 0.875 will be 0.875 into 256 will give us 224. Okay, 224, fine. दूसरा हमने देखा 570, 10 से गुणा करेंगे, right? 570 divided by 256, what will be this? 2.2265625, right? तो यहाँ का ये 224 में ऐड होगा, so this will be 226 कॉमा यहाँ बचा 0.2265625 into 256, so this will be what, minus 2 into 256, this turns out to be 58. Okay, so this will be 58. Are you getting me? Any question?
No, sir.
So are you able to complete the calculations?
Yes, sir.
So what is the final answer? Should I leave it or should I complete the whole thing?
So we can carry it by ourselves.
Okay, so maybe I am not showing this rough calculation. I will write down the results, right? When we do 3 okay, forget, we need to add 4 also, you know. This will be 1 2 2 6 and then it is 62 base B, and input is 3 multiplied by 10 multiplied by 10, so this will be 18 214 108 base B and add 3 this will be 18 214 111, okay, base B. So next input is 2 multiplied by 10, so this is 188 96 86 base B, add 2, this is 188 96 88 base B, input is 1 multiplied by 10, this will be 7 comma 91 comma 198 sorry 195 comma 112 base B multiplied by 10 add 1, this will be 7 comma 91 comma 195 comma 113 base B. So essentially we have the result now that 1 2 3 4 5 4 3 2 1 in base 10 the same thing as 7 comma 91 comma 195 comma 113 base 256. Got it? So this is how we do the conversion. Okay, so now I have to ask you one question. These, have you heard of IPv4 or something like that?
Yes, sir.
Yes, sir.
Do you see any connection with these things? 256 base in IPv4. So IPv4, you know, things are base 256 only actually, you know. So so you can actually convert any IP address which is written in base 256 back to a decimal number. So I leave it as an exercise for you to check that, you know. Anyway, I think so if I ask you base 256 number is given to you, and if I ask you to convert it into decimal, how will you do that actually?
Multiplication.
You can multiply by, you know that इसमें इकाई दहाई से इकाई कौन सा है, right? दहाई कौन सा है? मैं तो हिंदी में बात करता हूँ शुद्ध, right? So you can just do all these calculations, right? So basically 19 34 230 113 base B. Suppose this is given. Show that this is 321054321. Okay, I leave it as an exercise for you to verify. Okay, so you can just do this conversion of one base to another base. So this is something. Why I have chosen base 256, because this is quite useful. Any idea why 256 is important? I told you about IPv4 application, but apart from that, yes. अरे बोलो ना, मेरे को तो तुम लोगों को सुनना है basically.
Sir, I think 256 encryption hasn't been broken yet. Maybe that's why.
Well, I mean, that's not correct. It depends. In the hash value thing, those things are there. But first of all, 256 means power of 2, right?
Yes, sir.
And 2 raised to 8. So 8 bits are sufficient. So you remember byte. You might have heard byte,
Yes.
right? Kilobyte, megabyte.
Yes,
So
sir.
byte. So data representation is done. A lot of these things are in byte. So if you have a doc file, PDF file, Excel sheet, PPT, PowerPoint, these things are converted into byte strings, because ASCII values are from 0 to 255. Okay, right? They are from 0 to 255, right? So 256 values are there.
Yes, sir.
Okay, so that's why it's very natural, and this is a field. There is a field with 256 number of elements. You can do addition, subtraction, multiplication, division. Okay, you can do all the 4 operations. So that's the reason, our bytes are very, very important. So this is 256 based representation is quite useful. So you will see that actually, in many calculations, so many times we do binary representations. 256 representations is quite common, and of course decimal is what we do in our daily this thing. But the base B representation 256 is very, very important. Why I am doing all this? Later on, I'm going to ask certain questions like, if I want to add 2 numbers, okay, in base B, what is the complexity? How fast can we add? So how fast can we add 2 numbers? How fast can we subtract 2 numbers? How fast can we multiply 2 numbers? How fast can we divide 2 numbers? So all the basic arithmetic I'm going to do with the complexity theory. I would like to show you that how fast we can do. Okay, and there are, for example, I think addition and subtractions are anyway, they are not so basically n digit number is there, so the complexity is order of n only. There is not much benefit. I mean, that is the best or optimal you can do, but multiplication can be improved. So normally the multiplication that you know in your high school days or something, it takes order of n square, right? But that can be improved also, using a technique of multiplying complex numbers and so on. There are nice algorithms available. There are many modifications available. As recent as 2008, 2009, people have given algorithms for multiplying 2 integers in a fast way. I think you can also think, if you can think of a new algorithm for multiplying 2 numbers more fast, right? So so basically, when we are looking at the complexity theory, the first thing is we look at the arithmetic. So that's why I'm doing this base B arithmetic for you. So today I've told you about the conversion. In the next class, I am going to look at the other arithmetic: addition, subtraction, multiplication. By the way, when we are going to do the next class, the Friday, everybody is busy, or what is the issue? Friday, are you busy, or something else is there? At the time, that we have the time, is there a, I think some of you told me that there is a tutorial, TA-ship, right?
Yes, sir.
So at what time you want to do the class?
After 1 p.m.
We also have a free slot from 10:15 to 11:30.
10:15 to okay.
But sir, our TA duty is from 11 to 1 p.m.
Okay, 11 to 1. So what should we do it on Saturday?
Yes, sir.
Saturday is fine.
Sir, can we do it from 1:30 to
Friday.
2:45
Yes, sir.
1:30.
One.
Yes, sir.
on Friday itself?
Yes. Friday.
So rather than keeping 1:30, because normally it's a lunch time, should we do it at 2?
Yes, sir.
2 will be fine.
Will also be fine.
Any issue
Yeah.
with 2? 2 is okay with to everyone?
Yes, sir.
Yes, sir. Yes, sir.
ओके ठीक है, तो फ्राइडे को 2 बजे फिर मिलते हैं, ठीक है ना? तो
Yes.
ठीक है. सो आई थिंक आज का इतना ही है. सो आई थिंक आज हमने आपको एक्सरसाइज भी दी है छोटी सी, राइट? ये कन्वर्जन की एक्सरसाइज दी. मैं डेली एक्सरसाइज दूंगा और सम टाइम ये एक्सरसाइज में एग्जाम्स में ही पूछता हूँ. तो आई थिंक अगर आप करते रहोगे तो अच्छा रहेगा. ठीक है,
जी सर.
तो ठीक है, आप करते रहोगे साथ साथ तो अच्छा रहेगा. फिर बाकी हम अभी कॉम्प्लेक्सिटी के नोटेशंस भी कवर करेंगे और बेसिक चीजें कवर करेंगे. तो स्लोली विल बिल्ड द कोर्स. ओके, डिपेंडिंग अपॉन योर बैकग्राउंड I will go deep. By the way, one more thing is there. You need to have which OS you use, Windows or Linux or Apple or what?
Sir, somebody.
Windows.
Windows. तो बेसिकली ये पेरी जीपी सॉफ्टवेयर जो है ना, उसको डाउनलोड करके तुम लोग प्ले कर सकते हो. मैं I can show you few things. Actually, you can play with the numbers easily. पेरी जीपी करके सॉफ्टवेयर है, मैं लिंक भेज दूंगा तुम लोगों को, ठीक है? डाउनलोड करके, because then you will see reality, doing certain things. ऐसे तो हवा में थ्योरी हो जाएगी and you don't know what is going on. Okay, ठीक है?
Yes,
Any
sir.
questions? Any questions for today class?
Sir, have you created Google Classroom? Last time you were saying.
Yeah, Google Classroom तो है ना. 1 minute, let me send you the link right away actually. So stop sharing. Let me. उसमें 3 लोग तो है ना ऑलरेडी. मैंने शेयर तो किया था.
Yes, sir. You have shared.
I guess. Copy the link. Cancel. I'm again sharing this link. Okay. Google Classroom. Now you can join. Okay, इसमें 3 ही लोग हैं अभी, ठीक है? मैंने पिछली बार वो डाल दी और ये सारे जो मैं करता हूँ, राइटिंग करता हूँ ना ऑनलाइन क्लास में, ये मैं वहां पे डालता रहूंगा. सो यू हैव ए रेफरेंस, राइट? ठीक है?
Yes.
Yes.
ठीक है. Okay, thank you very much and see you in the next class. Okay?
Thank you, sir.
Yes, sir.
Thank you, sir.
Thank you.